ZGlue. It's really exciting to see students here also.
Yeah.
So my name is Jawad. I am the CTO of the company. So ZGlue is a technology out of Stanford University. And one of our advisors is very famous in Japan. His name is Professor Yoshio Nishi.
Oh.
So he's one of our advisors. And the background of the technology is in 3D integration of chip stacking. So if you look at the name, it's a glue chip that allows you to glue different chiplets in the Z direction. So how has introduced the company? I will take you a little bit deeper into some of the technical details. So what we are showing here is the history of semiconductors in a way. So traditionally what we do is we build integrated circuits, ICs, we put them on a PCB, and over a period of time, we combine some of these functionalities together to make SoCs. All of these ICs have a single chip of silicon wafer, right? So this is what has been called homogeneous integration. It's just everything is on a single wafer. The problem with this approach is single wafer technology has limitations. You can optimize it for logic design or MEMS or analog, but you cannot optimize it for everything, right? That is where the new concept started. The new concept is heterogeneous integration. So if you look at the roadmap of semiconductor technology today, they are actually moving from homogeneous integration to heterogeneous integration. And there are different types of technologies being developed for these. So on your left-hand side, you see what has been referred to as a 2.5D. In this technology, there is a silicon interposer, which is a piece of silicon, and then you have multiple dies. Usually one die is a microprocessor, the other die is memory. So high bandwidth memory, this actually has been shipping in the server market. So the silicon interposer, it only provides a lot of wires going from die 1 to die 2, maybe a few thousand wires. So, and then this combination is put onto a substrate, and you see the package. That's the microprocessor going in servers. That then goes on the server PCB. So this is really good technology for high performance applications. And one of the challenge here is that silicon interposer, it costs additional money. And these technologies have been a little bit more on the expensive side. But if you need performance, there is no other solution. That's the direction. There's a lower cost variation of it that is called system in package or multi-chip modules. That's where you take multiple dies and then you put them onto a fine pitch substrate. You can make the substrate really, really fine pitch, but its cost starts going up and starts becoming like that. So for cost considerations, usually these are the type of solutions that are available if you want to make a really small module. This is the direction that people have done. One of the challenge with this one is if you want to build it, you need to know somebody like ASE. If you are a startup, ASE doesn't want to talk to you, right? Because they only want to provide this kind of technology to Apple. This technology has been used in Apple iWatch quite a bit. So then comes the next generation. The next generation is the ZGlue concept. The ZGlue concept is that we have built this ZGlue chip, which has two things in it. It has an interposer, which is connectivity that allows you to connect different chips together. It also has chip functionality. It has voltage regulators, a little micro sequencer, and a few other things that I will show you. Okay, so what happened here, this chip, ZGlue chip, is not just wires, it has more functionality. So if you put the voltage regulator in here, you don't need to buy an additional one. So from cost point of view, it actually starts becoming very similar to that one, but it is more suitable for wherever you are developing something and you are cost sensitive. So you can take this hybrid, which is ZGlue plus these other dyes, and we provide this in multiple packages. We can provide it in BGA, QFN, LGA, and what you see here is a chip on board. It's direct attached to a PCB, right? So this is the very high level concept of how does ZGlue fit into heterogeneous integration. And the truth is that the same technology has big application in the server market. So 2 days ago, there was an announcement by Open Compute Project where Facebook is a participant and ZGlue is also participating in that one. So before I tell you a little bit more, this is what we call the ZGlue integration platform. Chiplets that come from other companies like Nordic, Dialog. We have a list of 22 right now in our beta. But if you log in, you will see 120. And then pretty soon we'll have 500 or so chiplets that will be available to public. And we are the first company that has the chiplet market available to other companies to use and build these kind of heterogeneous systems. ZGlue Smart Fabric. So this chip, I'll show you a little bit more what's inside here. You will hear the term Smart Fabric or programmable silicon interposer. So we don't have to really draw the wires going from one point to another. You actually, just like you program an FPGA, there is a tool that we will demonstrate. You do your connections and you generate a binary file, you download, and that makes connections. So if you put this thing under a microscope, you will not see any wires. That is what gives it, makes it difficult to reverse engineer, right? Because all of this is in the software. Okay, so as I mentioned, we have it available in multiple form factors. Chip on board, chip on glass, something like that. If it goes on a QFN or LGA, there's further packaging. We can put solder balls on it, and that would also look like a ball grid array. So let me dive deeper into the ZGlue Smart Fabric. So previous diagram was a cross section. This is more of a three-dimensional rendering of it, where you are seeing multiple chiplets that are put on top of a ZGlue Smart Fabric, and then it goes on to another LGA substrate. This particular diagram is for an LGA substrate. So I'll show you the block diagram of what's inside the Smart Fabric, but at a very high level, it does have routing, which is programmable, and it does have multiple types of routing. There are analog routes available, digital routes that are buffered. We also have developed a technique to handle radio frequencies. So Bluetooth Low Energy has been already validated. So there is radio frequency routing. You can talk to the ZGlue Smart Fabric using SPI or I2C from outside, or actually also talk to it from the top. It does have different types of voltage options and different types of in battery management option. And then we have the ability to use push button controllers, LED drivers, GPIO expanders, programmable IOs, and programmable resistors. We do have a few programmable capacitors. So for termination of signals, where you need parallel resistors or serial resistors, we have that built in, and we can get to within 5% of the defined value by using a trimming methodology. So let's see, what is the benefit of having programmable routing? That's actually a very important question. So let's say you're a small company and you built your device here and you want 10 units. You want a prototype. So at this stage, you really are interested in time to market. With this methodology, you will get your 10 units in your hand. If you go on our shuttle program, you will get those in hand within a month. You can ask us for another 1,000, 10,000 units, we can build those. But let's say your product takes off and you need 1 million units. We actually have a path to move from the programmable routing to what is called a structured zip. If you come from the FPGA background, FPGA companies give you an FPGA option. If you go to volume, they have another product called structured ASIC. The same programs that you've developed you will be able to migrate to the other one. You can go get to high volume manufacturing. So we worked out a flow where you start with the programmable routing, get to 10,000, 50,000 units. If your volume is going to millions of units, no problem. This will give you a path to a cost down or performance improvement type of design. But that's a question of NRE cost. Okay. So the other thing that happens, as we know with FPGAs, if you make a mistake, it's very easy to fix it. Change the program and try that again. So it gives you quick iteration ability, right? And then the other thing is, in some of these markets that we are targeting, like Internet of Things, battery life is important, right? So how do you extend your battery life in a chip? If you look at the microprocessors, those guys have developed lots of interesting techniques. There's one called dynamic voltage frequency scaling, where they can change the voltage and frequency of the microprocessor on the fly. And they have another one called power gating, where whatever they don't use, they just shut it off, right? If you try to do any of that type of thing on a printed circuit board, you will need to buy additional chips, right? What we did is we embedded all of that in here. So for the first time, if you are a better designer, you can now dynamically change the voltages of different rails. You can do power gating, which in this context is called load shedding. So the other thing, what we call bill of material reduction. So let's say if you're using the LED driver built in, you don't need to buy that chip separately. If you're mixing and matching chips for different voltages, you don't need to buy the level translators, they are included. So what happened here, if you are an electrical engineer or a firmware engineer, we are showing you a new way of designing your system, which is traditionally only available to chip designers who work in big companies like Toshiba and Sony and have tons of budget available and time available for them. So by doing this thing, we actually brought it to people, right? That now, if you are interested at the board level, you can actually design your chip, right? And you will see that once you make it easier to design, it also plugs into the software development very naturally. That's something that we will demonstrate today. So This diagram was not very clear, especially for people sitting in the back, so I zoomed it in. This is the block diagram of ZGlue Smart Fabric. So I will explain. Yeah. So this particular piece is the surface, so physical surface of the chip. I'll show you the actual microscope pictures in a minute. This is the programmable routing. So you put the chiplets on top, and that's how they kind of get connected. So this is the routing matrix. Inside the chip, there are all these other things. Like I was saying, there's integrated voltage regulators, LDOs of different kinds that generate anywhere between 3.3 volt to 1.8 volts, 2.5 volts. We have boost converters, system level LDOs. Our next generation will have buck converters. This particular design can handle up to 500 milliamp. For this particular design, we have other things in the works as well. Now look at this one. There are on-off controllers with switch debouncers. A lot of these devices, you need a little button. You want to press a button to turn it on and off. That circuitry is built in with different timer options that you can select. It also has, like we said, LED drivers, which can control the color of the LED. Also have a one-time programmable memory. So whenever you design using the chip builder, you design, hey, this chip is connected to that, and this chip is connected to that. All that information can be stored here. When chip boots up at time t equals 0, it reads all the information from here and comes up. And then it hands over the control to the main microprocessor or main microcontroller. And then from there on, the main microcontroller firmware takes over, and that can override what's written in here or part of it. That's also something that's the foundation of over-the-air update. And that's also a technology that we have developed and validated. If you look deeper inside, you will see a fabric controller that kind of controls the connectivity. There is built-in self-test. You have the option to talk to this chip from outside or from the top using SPI or I2C. As we said, there are lots of programmable resistors that you can put into your schematic. You can expand GPIOs. So a lot of these embedded devices have constraints because the number of GPIOs are not sufficient. So here you can use the trick that you can take one GPIO, multiplex it for different applications. And the same thing with, as we mentioned, level translators. And then you need to learn how to design with this thing, right? Because it's a little bit different than conventional chip design or conventional PCB design, right? So, but it's not that hard once you understand the concept, right? It opens up a totally new dimension of development possibilities. And like Hal was mentioning that, you know, we did some of these power systems in there. So here's a one very simple example. The voltage regulator that we put in there. It generates multiple rails. You can individually control the voltage of each rail. See 3.6, 3.7, 3.8, or you want to bring it down 2.7, you can do that. And when you change those voltages, you potentially can save on power. You can completely cut them down, cut them out. So you have load switches both on power and ground, optionally, and also IOs. So you can build a system that can completely isolate some of these chips, right? So, and we make all of this available to the developer through firmware APIs. So you don't really need to know too much about circuit detail, you just need to know how to use the firmware APIs to control these things. This is the power tree that we have right now, which is three main LDOs, one boost converter, and one high voltage system level LDO. We can configure the system for a 1 volt battery, which is the zinc oxide type of battery. We can configure it as lithium non-rechargeable, or we can configure it as lithium rechargeable, right? So there are multiple modes that you can configure this thing in. So I will probably skip these ones a little bit and show you one or two diagrams. This one is, I think we have a demo here, right?
Yes, we'll have a demo.
Yeah. This is actually microscope picture. This is a system which we call Chicago, is our internal name.
Third generation.
Huh?
Third generation. Apollo.
Yeah, this is the third generation. Right. And this particular chip that you're looking at, what you see is a micro, and then a accelerometer. There's a real-time clock. That is a MEMS clock. Then there's a heart rate, PPG, AFE. But the interesting thing is, this particular one is a chip-on-board configuration. See, this combination is directly bonded onto a PCB. It can be bonded to a flex PCB also if you want really compact thing, right? You can actually reduce this size further if needed. You can, and if you look at the profile, the thickness of this one is like less than a millimeter. So ZGlue only adds up to 100 micron. The rest is determined by the chiplets that you put on top, and there's a possibility to grind it down as well. This can potentially give you a lot of compactness, right? There's a variation of this which we call OmniChip that Hao was mentioning, that's available to purchase. So those are the chips, and we have a data sheet available for those. Now just imagine that the ZGlue chip is constant, but you have multiple combinations of chiplets. So you can produce a lot of different types of products using the same baseline. This one is one generation ago. This one was called Austin. This one has dialogue, semiconductors, microcontroller, and Bluetooth. It has flash memories. In this one, it had a different type of EKG monitor. And this one is built into an BGA package. So this particular customer wanted this thing to go on the BGA, so that's what we did. But the ZGlue piece is like, that much.
So please, yes, thank you.
Yeah, go ahead. People could buy this one last year, I think. Yeah. We sold these online. So there's a whole dev kit that goes with it. So when we show you the demo, this is what you will see. You will see basically two steps. Step number one is you select your chiplets. So figure out what do you want, and then there is a canvas. You drop them on that canvas. That's the stacking part. So it's basically the development piece. At that stage, you can create your schematic, you can do the routing, and you can download a SDK. You can buy a dev kit. You can start your development. And if you like this thing, you can place the order either through shuttle program or through volume, and you will be delivered these kind of chips. We are not doing the industrial design. That's your job. You build your own mechanical design. You do your own application program. We provide you support. We provide you examples. That's something that will show you, like how using our SDK, you can plug into Alion or maybe tomorrow into Google Cloud and things of that nature. So let's see. I'm gonna tell you guys something very technical. Okay, so So just bear with me, but it's a important thing, especially if you're from a university, right? This is kind of like the heart of the technology, what made it possible for us to disrupt the market. One of the challenges, so what you're looking at is the very first thing that we did at Stanford University when we were sitting in the incubator. And this is an X-ray image. What you see in here are the solder balls on chiplets. These chiplets are wafer-level chip scale packages. You measure the distance, you will see it's 400 microns. In some cases, you can buy them down to 100 micron, 200 micron, but generally, the ones that people sell to go on boards are kind of limited to this. So you cannot go out there and ask people to create a special chiplet that is very standard. Every other chiplet has a different footprint, right? No two chiplets will have the same. There is an effort by a number of companies right now to standardize it, but it's gonna take another 3-4 years before it gets standardized. So here is the technique that we have come up with. What you are seeing, if you pay attention to this picture here, you will see that there are big circles, and then there are really small dots. There are lots of those dots. Each one of those dots is what we call copper microbump. So those are at 100 micron pitch, and there is active circuitry underneath. So the technology that we developed is what's called one-to-many solder to copper connection. So what happens is that there is a discovery mechanism inside the fabric controller that knows what to expect, and it actually measures what was built. It compares the two, and if it has to make any adjustment, it will make the adjustment. So we now have a lot of experience validating this technology at multiple manufacturers. And what we have learned is some of the manufacturers are so good, we don't need to do any correction. But some other manufacturers, we can correct the design variability, manufacturing variability by using software. So this was the foundational IP of the company that enabled us to take chips from multiple companies and be able to use it on a standard glue chip and push the hardware complexity to the software side of things. Sorry for the too much technical detail, but for those of you who are interested, I think this one is important. And this is really the only thing that where I go deep into this. One last thing before we kind of stop for questions is the chip builder. Chip builder is a cloud-based software that we make available. So you as a developer can actually develop chips by creating an account on Chip Builder. So it has multiple things. We have obviously the customer facing thing, which you will see where you actually are designing the system. But behind the scene, it does many other things. It's actually kind of connected with our manufacturing partners. Whatever data gets generated gets transmitted over to them. It also plugs into the silicon design that we have underneath and the system constraints that we have in there, or the manufacturing constraints. Design rules are built into it. There are rule checks and things of that nature. Only one caveat. Chip Builder today is in beta. It's not 1.0 yet, right? So at CES, which was 3 weeks ago, we opened it up for enthusiasts who want to try it and want to build something with it. Today, you are limited to 20 some chiplets, which is not too many, right? but at least gives you an idea of how you can play with it. And you will find errors. Please tell us what problems you're finding. That would help us, and will in turn enable you for 1.0. And if you really are interested in building something, we can actually enable more chiplets for you. If you have volume forecast, or if you have a very specific requirement. There are some customers who came to us and it's like, this is great, we really need to have these additional things added to the library, and we accommodated all those situations. So what happens is, if you think about this one, we are automating a lot of the complicated things, and that's how, with a very small team, we are able to address a variety of customers, which is automation. That's the key. I'll skip this one because I talked about it a little bit. We have our list of partners keeps growing, right? Which is people who provide us chiplets and all the manufacturing and design and supply chain. So you can visit our website and you'll see the more updated list there. Before I just finish my talk, I will reiterate. So how I already went through this slide. Designer designs a schematic, picks the chiplets, they do the place and route, and from there on, we as ZGlue get it manufactured, and we deliver it to the customer in a chip format, and the customer then designs their board. We do have reference designs available here. We do have reference designs available there that you can start with. And my last slide really is about the firmware piece. You will see more details, but these are the main components. We provide you firmware APIs. If you have your own SDK, or if you have your own SDK that's your favorite, you can just take our firmware APIs and we can help you build the firmware using your SDK and our APIs. Just all the calls that essentially enable, control of those voltages and routes and whatnot will go into a little bit more detail there. Then we also have a SDK that is actually open source. So we ported nanoPower operating system onto a family of ARM Cortex M4, Nordic being one of them. So, and we provide the whole development environment to go with it. You guys are welcome to use our SDK and build with that. We also have some of the sensors that we provide in our library. We have the algorithms to go with that. And just say one last thing about the ZGlue SDK. If you choose to use our SDK, you have all these benefits. There's a tool chain available. You can use the tool chain on pretty much any platform. You don't need to buy Kyle. We are based on GCC, and we're using nanoPower, which is a pretty liberal open source license. You can use that one. Obviously, it comes with a file system in it. There is connectivity support of various kinds, and all the APIs that you need to talk to the functionality in ZGlue chip are integrated into the ZGlue SDK, should you choose to use that one. So with that, I'll take questions. And
okay, may I have one question about the firmware. API for the firmware.
yes.
Yes, please show me the slide. Yes, this one. I understand that the smart fabric has functionality for routing of the chiplets. And do you mean that the main controller which you can control the routing of the on the smart fabric dynamically.
Yes, you have two options. One is the static programming, which is what you do with chip builder. You say these are the routes. You put them in one-time programmable memory that helps it boot up. Once it boots up, then you have the dynamic control that's available to you. And that's where you can use the firmware APIs, and you can do a lot more things that otherwise firmware engineers can't do. Right? It's a good thing and it's a bad thing. The good thing, it gives you a lot more power, but you can make mistakes too. Right? But once you learn how to program with it, it opens up new things. That's where Hao was mentioning that we can do new security things, which is look at the signature of the chiplets, hash it, and figure out if this is the correct system. And right.
すいません、誰かこれの API とかデベロッパーツールはライセンス料かからないか聞いてもらえないですか？
In this firmware API and SDK is license based or free to developer?
Free.
Thank you.
Yeah, and maybe updating many times on the market on the website.
Also in the field also.
Not open source proprietary, but managed by your company, but update very immediately, and also share to the whole of your customers.
Right.
Any people using only one program to any your customer using only one SDK and only one API, no version, no like light version or professional version.
No, it's just one thing.
Yes, one thing.
It's just one thing. No professional, no light. It's the same. But your choice.
Yes.
It's the choice of the customer. Right? If they want to use just our SDK, or do they only want to use the APIs with their own SDK?
Yeah. By the way, our SDK is actually a BSD license.
Oh, BSD license.
Provides pretty much the best protection for customers. If you're using other folks' SDK or whatever, you don't know. Sometimes it's hidden weird license over there.
So I think that it seems the more integrated approach rather than the legacy one. But my question is, what is your main point of your patented technology? Patent pending technology.
Not patent pending, we patented the technology.
Patented.
Right.
Sorry.
So it basically allows us to use the one design for many applications. Right? Right. Because you can, if you want to harden the design, let's say you go to volume, we can remove, that's the concept of structured set. That if you don't need the programmability, you can remove all of that, and you will still be able to use the same programs that you develop. So a lot of the infrastructure stays the same, but you can choose if you want to improve the performance, reduce cost. That's all a question of NRE at that stage.
Yeah. I felt a very great idea how to, it's a very, I think, coolest idea how to use FPGA.
In a way, we don't call it FPGA, this is the ZGlue way of doing it, right?
Yeah, very coolest way.なんか FPGA だけじゃないかもしれないけど FPGA も使ってマザーボードを作ってることですよね。言うなればマザーボードっていうかスマートブレッドボードみたいなものを作ってるってことじゃないですか。でだからその IO のベースとして FPGA を使うっていうのはすごいいいアイデアだなと思って、普通あれに全部やらせようと思うじゃないですか。
FPGA の中にあるルーティンのところは FPGA のままにしておいて、ロジックブロックがチップレートなんですね。
そう
マイコンだったり線の位置だったり。
ベリークルアイディア、ベリークルアイディア。
さっきの説明からすると、外のピンの、01でもって決め こういう機能にしろとかああいう機能にしろってできるってことですよね。
それがここからコントロールできる。動的に変えることもできる。FPGA がさらにカスタマイズは、FPGA に乗っかるロジックブロックが変えられる。
だから一個一個のその技術コンポーネント自体は言われれば確かに今あるものなんだけど、この使い方でしたっていうことには特許が発生すると思うので。
高さんが言った例えば一番多分的確で、ブレッドボードに部品IC さしてジャンパーワイヤー配線するわけですけど、その部品がチップレットで、そのジャンパーワイヤーがそのスマートパブリックの配線で、それをジャンパーワイヤーで飛ばすんじゃなくて、僕らまで設定できる。
でだからそうダイナミックなこうつないでるのを小さくし直す。
そのスマートファブリックが多分コアテクノロジーで、スマートファブリックがパテンテッドで、もちろんそのsome part of technology is understandable and part of technology is we very know, but in this integrated product smart fabric is sounds really unique and very great idea. That's a very agree to patented technology.
チップの上にチップを乗っけるの中なんだけど、そのチップの下のチップが、ルーティングが動的に変えられるっていうのが本当にSIP 練習ではあるんだけど、その SIP の中のチップのチップのさらにそのチップのチップの下がキーなんで。
Yeah, programming processor is a very known hardware. Chip on chip is also known hardware, but in combine is a more opportunity, and this one is an idea.
How do you protect the other copycats, right? Smart fabric is a key source of this type of innovation, but I would like to know that how do you protect your originality?
I think your question is our customer, how do they protect their originality?
No, your company protected. Like other company making the copycat smart fabric and copycat your business.
International patents.
International patents.
Right, so we have patents in multiple countries.
And also customer base and also the net connected to the many company.
Right. If you go to some of our partners, they would know that this is the patent technology.
Like I think ZGlue user like me is no care about patent or no care about patent Shanzai or authorized is both okay. But like Nordic, the TDK and maybe some sourcing service from them is very care for the patent.
Yeah, I'm a BD guy. So
Yeah.
But, in some cases, some conflict happens because hey, this type of approach reduces the BOM cost. But, in other words, for instance, say TDK guy say that okay, so this might be conflict with each other, but in such case, but even though that situation, the virtue of the partnership happens, so that's a very interesting.
Yeah, I think if I building my company and I steal of the idea of the smart fabric, probably I can making smart fabric, but I can make contact with the them sourcing service because they are big company. They are more care for the law and maybe the regulation. I cannot getting the cheap. If I can make the own Shanzai smart fabric, but I cannot getting the tip from Nordic, tip from maybe some company. Not patented, but not only patented.
Yes. There's a lot more in here because your IP as a customer is stored in the one-time programmable memory, not easy to reverse engineer. And then there is a whole bunch of other know-how to go from the programmable to hardened version.
あと今現在までの開発量も結構多いと思うんですけど、だからここに来るここまで来ただけの開発量がまあまあ多いから、2人とか3人の会社がコピー作るのは多分無理で、とかでっかいパワーを使おうと思うと、そういう会社がシャンザイってやりたかったりするじゃないですか。大して儲かんないしっていうのがあるから、うまい守り方だなとは思います。いや、like big company patented and big company network and also your legacy of the software and hardware, many knowledge in your company already. If the 5 or 6 people building the company and against what they can know, but maybe the 100 people the company they cannot doing the Shanzai business.
Thank you so much for your time.